Okay, today is 9.3. It's about infinite geometric series. Why don't we talk about infinite arithmetic series? Because watch, here's what it would be. 1, and then I add 2 and I get, not 2, and I add 2 and I get 3, and then I add 2 and I get 5, and then I add 2 and I get 7. And do you get, if I do that to infinity, you can't add it up because it's just going to get bigger and bigger and bigger and bigger. But if I do a geometric series where I'm multiplying by something, let's explore that for a moment. 2 times 2 is 4, times 2 is 8, times 2 is 16. Will that kind add up to a finite amount, or will that also be an infinite answer? That would be infinite. So what is the one kind that we can actually add up? It's getting shorter and shorter and shorter, like me going to the door. I have to get halfway there, and then I get to do half of that, and those little amounts are getting smaller and smaller and smaller. So that's like starting with 16 and having it go down to 8, and then having it go down to 4, and then having it go down to 2. And it seems, though, like you're going to have an infinite number of things. If I go down to 1, and then I go down to a half, doesn't it seem like that shouldn't add up to a fixed amount? But it does. It adds up to a fixed amount. That is going to equal like 36 or something like that. So exactly what does it equal? Well, it equals, here's the big formula. Ready for the big reveal? S sub n is equal to, it depends on the problem, it's A over 1 minus R. Everybody write that one down. A meaning the amount you start with, and I've said about A sub 0 before, and then people get confused, but how come it's not A sub 1? Well, it depends on the problem. Sometimes it is A sub 1. So I'm just going to call it A for our starting amount. Even though the book refers to A sub 0 as the starting amount, I'm going to just start calling A. Just A, no sub anything, just A. That's going to be code for the starting amount. Because do you get, sometimes it starts with A sub 1? It does. And especially when you're counting for the third term, then A sub 1 is the logical thing to start with. All right, anyway, so we're just going to call it A. So then in this problem, it's A is the amount we start with, which is 16. So in this problem, it'd be 16 over 1 minus, and what's the R? In case it's not easy like this one, I know this one's easy, but you just take this and divide by that. What's 8 divided by 16? It's not 2, it's 1/2. So then I have 1 minus a half. With 16 divided by 1 minus a half is a half. And remember, when you divide by a fraction, it's the same as multiply by flip it. So this is really 32. So this one does add up to 32. Will everyone always just be double that? No, it depends on what rate it's going at. So let's do another one that's like that. 16, but this cuts down to 2 right off the bat. And then it cuts down to something really small, but I'm not going to tell you what. I'm going to make you figure it out. I want you to tell me, what is the third term of this geometric series? And then, what is the sum of all of them to infinity? Pause for a second. I'm going to give that a try. So when it isn't obvious that it's cutting in half each time. Mr. A, can you tell me what I did again to find that R? Yes, 2 divided by 16, which if I simplify it is what? 1/8. I hope you guys used 1/8 as your R. So then it's 16 over 1, again the formula was A over 1 minus R, so 16 over 1 minus 1/8. And don't let that bother you, it's just 8/8 minus 1/8, so then that's really 16 over 7/8. And again, if you understand these fraction over fraction deals, it's much easier to change it to 16 times, what? 8/7, and then I'm putting this over 1. And then you look for something to cancel, but unfortunately 7 doesn't go into 16. So we just have to tough it out and go 16 times 8. In case you're not good at this, have you seen me do this enough times where you go, it's 8 times 10 plus 6? because that's 8 times 16, right? And you can do it in your head. 80, 6 times 8 is 48. 80 and 48, 128 over 7. Raise your hand if you got the same thing as I did. Okay, awesome. That's what it adds up to. That's what this series, if you add it up forever, would add up to 128 sevenths. I know it's not very clean, but it's finite, even though you're adding an infinite number of things. Now, if that doesn't bother you, it should, because some of the best thinkers of the human race, it really bothers them that you're adding an infinite number of things and it comes out to something that's whole and complete. It's not like partway. All right, here's another one that maybe will bother you. If I had half of an apple, everybody gets that. You cut the apple in half, right? Boop, got a half an apple. Okay, and we all know the fraction for that. But what if I take an apple and I cut it into thirds? Okay, so imagine the top view. This is like the top view of the apple, and here's like the little stem thingy. And I cut it into thirds, and I have a third of an apple. Do you get that that's the same as 1/3, which is the same as 0.33333? And it seems like it goes on forever, but that it's somehow like how do you have a third of an apple then? It's 0.333. It's like part of it is going on forever? No, you just have exactly 1/3 of an apple. That this whole decimal going on forever thing doesn't mean that your part of your apple is changing, does it? All right. So if I wanted to say that this 0.3 repeating thing is really a sum of a whole bunch of little parts, you get how it's 0.3 plus 0.03, that's this one, plus 0.003. Do you get where I'm going with this? It's an infinite series that's getting smaller each time. The amount you add gets smaller each time. But do you get, it doesn't actually come out to something that's like goes on forever. It actually comes out to a whole thing. It's the third of the apple. So what is this? Well, when you actually take that plus that as a series and you do it to infinity, you get a formula for that. S sub n equals a over 1 minus r. Please use that to prove that that equals 1/3. That 0.3 repeating really comes out to 1/3. It's an infinite sum of little things, yet it comes out to something whole. A was 0.3 over R was 1 minus, what are you multiplying by each time to get it to turn to that, 1/10, or 0.1. And that means this is 0.3 over 9/10. So if I flip and multiply, three tenths times 10/9, that's this thing flipped, gives you 30 over 90, which is 1/3. That's why this really is a whole complete thing, 1/3. It's not like really close to, that decimal does go forever, but all those little parts, when you add them all up, do equal 1/3. All right. Now, for those of you that were doubters of the whole 0.9 repeating is actually equal to 1, would you please express that as a bunch of fractions being added together for infinity, and then use the formula I just gave you, and you can prove that 0.9 repeating is equal to 1. This is 9/10 plus dot, dot, dot. I'll pause for a second. Let me give that a try. Okay, I'm back. That spot right there is 9/100ths plus dot, 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 and it goes on forever. You keep doing that. So what was the starting amount? S sub n, amount over 1 minus r. So the amount is 9/10 over 1 minus, what was that amount you were multiplying by each time to go from there to there? 1/10. And this one becomes really easy. It's 9/10 over 9/10. And you all know what that means. And it equals 1. You add up all those little tiny parts, it actually equals 1 whole. It's not just close. It's not just, some people say, well, it approaches that. Nope. Doesn't just get close to it. Kind of like the asymptote line, you know, you get close to it and you never touch it. No, 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 no. It's different. It actually is. It's equal to. Yes? Yep. I'll give you another situation that's like an asymptote that you might be able to relate to. Imagine for a moment that you have a swimming pool. It's only got a little bit of water in the bottom. Okay, it's like got an inch deep of water. Okay, put a little eyedropper of nasty poison into the water. Okay. Now, put in more water. As a percent, the poison has become small enough that you're probably even safe now. But put in even more water. Is it gone? Is the poison gone? Add as much water as you want. You get how you get closer and closer and closer to perfectly pure water, but it will never actually be perfectly pure water because you have that little bit of poison added in there. It's kind of like that. There are things that can get close and close and never actually touch. It's like you can be close to a perfect person, but you won't be perfect. Can't be. I'm not a perfect person. Ever heard that song? Obviously giving life truths. So yeah, an asymptote's different. It gets close to an asymptote, but it doesn't touch the asymptote. But this is not like that. This is not like the limit approaches, let's say that's 10 up here. It gets close and closer and closer. It's so close to 10 that it's pretty much 10, but it's not 10. This is different. This is where when you're adding up all these little parts, it actually does equal it. And if it didn't, here's my best proof for you. I couldn't get out the door. Because as I get close to the door, I got to go halfway. And then I have to go halfway again. And then add another half of that. And add another half of that. And if you really never stopped because you just always got really, really close, then I couldn't actually get to the door. But look at that. Oh, I just did it. So if you're adding infinite smaller amounts, as long as you're getting smaller each time, multiplying by some amount, then if that wasn't true, that it would equal a whole, it equal a total, then I could toss this marker in the air and it would never hit the ground. Because, why? Because it would be getting, the amount of time it would take to eventually get to the ground would be infinite. Because you'd have to add all these little parts. It takes some amount of time to get the next distance, and some amount of time to get the next distance. And if you couldn't add up infinite parts and make it equal a whole, then this marker could never hit the ground. You want to be able to get out the door, don't you? Then you have to believe that adding up infinite parts can eventually lead to a whole number, a fixed amount. All right. So anyway, how can this stuff get harder? Well, sometimes they just make it harder to tell what it decreased by. 1/10 turning into 1/100th is a no-brainer. You just times it by 1/10, right? But what if it's 1/10 turned into 1/120th? So do you get that it's not so easy to tell what you multiply by? Well, actually, in this case, it's not that bad. But what if it was 1/11th turns into 1/123rd. Well, I could know that it was multiplied by something, but it was icky. What do? You take this and do what? Divide by that. So 1/123 divided by 1/11th. But that's the same as multiplying it by the reciprocal, which is 11, and therefore I'm going to change this to times 11/1. So it's really 11/123. Just don't forget how you can find that ratio in case it's not obvious, like, oh, they cut it in half every time. Take this one, the second term, and divide by that one, the first term. All right, here's another kind of problem that comes up a lot. Let's say I don't know the beginning. Some mystery numbers underneath there. But then the next number was 10, and the next number was 5. And if you're saying, oh, Mr. Server, that's too easy, because I can tell that the thing just got cut in half, okay? If it's geometric, then I would have to be able to say, okay, 5 divided by 10, you multiplied it by 1/2, okay? But what if I said it's not geometric? And then I must have been subtract 5. But that's assuming that there's only geometric or arithmetic. Oh, no, don't do it. Don't do it. What happens if you had to do both? Okay, well, that gets really icky. Okay. Or how about this? What if I didn't know this one either? I knew it was a geometric, and then I knew this one was like 8. All right. So there's your problem. It's geometric. I don't know the first one. I know the second one's 10. I know the fourth one's 8. My question is, what's the first number? And if I did this forever, what would it add up to? Well, first thing I think of is, oh, I better get equations out, because for me, equations are the way you solve something like this. I know I made this easy enough that you could hack it, figure it out in your head, and just, like, you know, go guess and check your way to figure out, oh, what must have been here, and therefore what must be here. But I want you to think about formulas. So since it's geometric, and I'm not doing the sum yet, I know that a sub n is a0, or you could just call it a. Remember how I'm going to start shifting to just calling that a for starting amount? I know that formula applies. Would you please write a formula using the fact that the second term is 10? That alone is not enough to tell us anything. Think about it. If I didn't ever tell you this 8, that alone is not enough to tell you what's going on. Just one number is not enough. But you can get a start. Think about where to put the 10 and what else do we know? Because there's 4 variables here. And at least I know 2 of the 4. Okay, Mr. N, what do I know? Something I know. Do you know the starting amount? No. Do we know, just by looking at the 10, what the R is? Therefore, you must know the N and the A sub N. So, tell me. This 10 is which term? And therefore, think about that. I know somebody whispered it to you, but think about it for a second. Does it make sense that the N is which term you're on, and the N is 2? Does it make sense now? Okay. So if that's 2, what's the other thing we know? We know 10. Where's the 10 go? Yeah. A sub N is 10. That's the answer, right? Okay, cool. So I got 10 equals A times R to the, I could simplify that and just say 1. 10 equals, that's a funny looking 10. Try that again. 10 equals A times R to the 1, or just A times R. And you might say, but that doesn't tell you everything. No, it tells you an equation that's got two variables. Do you get, if I had another equation like that, that also had those same two variables, that then you'd have two equations and two variables and you can solve for that? It's kind of like back when you were in algebra and they had x plus y equals 10. 2x plus 3y equals 12. If you have two separate equations that have two variables, you can substitute one into the other and solve. Okay, it's not that big of a deal. You can find the answer to this. This is an equation that has a line for this and a line for this, and these two lines cross somewhere, and that's the answer. Okay, so back to what we were doing. That is a good start. So take a wild guess what we're going to do to finish the problem. Same process with the 8. Why don't you tell me what it is? We'll just jump right to the answer. A sub n equals a r to the n minus 1. So in this case, n is 4, and that's an 8. So 8 equals a r to the third. Okay. So now, this one's really easy to solve for stuff. You can either solve it for r or solve it for a. Either way is pretty easy. Okay, why don't we solve it for a? Would you agree that a would equal 10 over r? So then I could stick that right here. Times r to the third, and ooh, some stuff's going to cancel. Eight equals, and that r on the bottom cancels with 1 on the top, 10r squared. Then I'm going to divide both sides by 10. 8 tenths equals r squared. And then what's 8 tenths really? It's 4 fifths equals r squared. And then if I'm going to take the square root of that, I got square root and the square root. And I get r equals square root of 4 fifths. True or false? False. What did I do wrong? Absolute value. Why does that matter? Because then there's a plus and a minus. Couldn't it have been possible that this was multiplying by a negative number? Because then when it multiplied by that same negative number again, it became positive? Aha. Math actually works. All right. So there's my two answers. I actually know the square root of 4. It's 2. So I could say plus and minus 2 over root 5 equals r. And some people don't like having a square root on the bottom. And leaving it that way is called having it. You can't have a irrational denominator. And so I'm going to multiply both sides, or top and bottom, by root 5. And I'm going to have 2 root 5 over 5. And it's the same, it equals the same thing if you used a calculator, you'd see. And that's the two rates that could have been. It could have been positive that, could have been negative that. Yes, sir.
Could you have just like plugged 8 for a sub n and 10 for a?
Okay, hold on. Okay, could you have plugged in 8 for a sub n? Absolutely. In fact, we did that right here.
Yeah,
and then
10 for a.
And 10 for a.
And then make n 3.
But that's saying that a is 10. Is your starting number 10?
No, but
no.
The rate of change is changed.
You could find that. You could find the rate of change by that. Yeah, okay, I can buy that, but you'd have to adjust for the fact that you aren't on that a was not 10. All right. Long story short, if you did it that way, you better get the same answer. As long as you get the same exact answer, then you're good. There is more than one way to solve the problem, but I don't want to start telling people to just stick that in for a, because I'm afraid they're going to think then that when you're done with the problem and you have to stick a into your answer, that a is 10, because it's not. So it's sort of a shortcut that will work. But, all right. So that's where it can get more challenging. And right away, my first reaction, and yours should be too, is if they don't give you the a, you got to go back to an equation. We started with this equation right here, and we stuck stuff in it. Don't try to do it by guess and check, because we're not going to make an honors pre-calc test where you can just guess and check your way to finding that the answer's, it's not just going to be an R of 2. The R is going to be like the square root of 11 or something like that. Okay. So let's actually start some homework together. I think you've learned enough for today. And we will be doing more stuff tomorrow. But again, my intent is to leave you with tomorrow just stuff to do in class that should be able to be finished in class. Now, if somebody was going to be obstinate and not be able to do work in class, then I guess they'll have homework. But if you are willing to do work in class, I'll make it reasonable that you could finish it in class. Okay, and there is a bouncy ball lab, which that may be part of what we do tomorrow. Think about how a bouncing ball is kind of like adding up infinite parts. Do you get if the ball bounces, it goes to like half as high as it used to be? And then it bounces again half as high as it used to be? Do you get if the ball bouncing like that is like adding up an infinite number of little bounces, do you get that the ball theoretically would never stop bouncing, and yet it does? Just like theoretically I couldn't get to the door, but I do. Because you can add up an infinite number of decreasing parts and have it eventually equal a whole. All right, so here's assignment day 1. I know it comes right after assignment day 2, but anyway, here it is. Find this reddish looking page. And these are all doable. When they say ... that means it goes to infinity. Okay? So if we were making a sigma for this dealy bob, we'd say it goes from 1 to infinity. And if we were making a sigma for this, you get that we are adding each time, but that's only because of the sigma. These are like terms, 27, comma, 9, comma, 3. Do you get that that's a geometric? The only reason the add is there is because we're adding up all the parts. This one's a geometric. So what's the geometric one? It's A0 times R to the n minus 1. You got to know these formulas or at least be able to use them. And then what is our A0, or just our A? In this case, 27. So I'll stick a 27 here. And what's our R? Well, I can do that by doing that divided by that. What's 9 divided by 27? 1/3. Do you just, again, I just wrote you a sigma notation for this problem. It's going to infinity. So to actually add them all up, I'll have to use this thing. That's so bad. And by the way, it doesn't ask you to do a sigma. I'm just trying to show you that you can. To add them all up, that's what you have to do today. You'd go A over 1 minus R, and the amount we start with is 27. 1 minus R. R in this case, 1/3. Pretty easy actually from there. 1 minus 1/3 is 2/3. If you know how to handle 27 divided by 2/3 is just a flip and multiply. Piece of cake. All right. So I just wanted to take a second and show you how that could be made into that type of a problem. Yes, sir. So you want this to have a 1 where? Oh, is this a flood problem? It could be. 1/3 of that. 1/3 of that. Yeah. Oh, wait. Yeah, it should be 1. Yes. Yes, it should be. I don't know. I don't think anybody's ever noticed that before. I think the teacher was typing it up and just oops. You know what it means? When you go from 1/3 of 3, you should go to 1, and then you go through to 1/3 of 1 is to 1/3. And you know why nobody probably ever notices that? Because by the time you looked at the first couple, you knew that it was times by 1/3. 12 minutes left. And then you don't need to have all that other info, right? All you need to know is it's times by 1/3, and you start with 27. See what I mean? So yes, it's definitely a flaw, and we will fix it. I'll put a 1 right there. But it's not necessary to actually answer the question other than to clarify, did you really mean it's actually going down 1/3 each time? And yes, we did. Okay, I'll get that fixed. Moving on. We're doing this whole page. And this page, these two formulas are going to be needed to answer number 5. We talked about one like that in class. If I were you, I'd write them down. Just make sure it's fresh in your mind. Those are the two formulas. Because it tells you the sum is 64. Well, obviously that can go here. And that's going to give you an equation that's got two variables in it. And this one is a different equation. You can stick in the stuff we know. The second term is 12. And we can stick that into this equation, and we'll have two equations that have two variables. And you've got to be smart enough to understand that now in honors pre-calc, that it's okay to have two variables as long as you have two equations. Then you can put the one in the other, and you can solve. All right. And yeah, we make these get a little more complicated. There's your first term. There's your second term. Here's your third term. And if you want to make sure that this is actually an R that's the same, you take this divided by this, and this divided by that. And can you see, just using your brain, can you see that that's actually true? I can, because it's 1 over that, which is this. And then it's this divided by 1, which doesn't do anything, and therefore, oh, it actually works. Cool, I know what the R is. All right, these are good thinking questions. Moving on. This one's also assigned. It's arithmetic, though, this time. Be careful of that, because if it's arithmetic, that sum to infinity thing doesn't apply to it. And that's it. We get into giant ants tomorrow. Okay, the rest of the time is yours to work on this.